Alright, y'all, I am back with part 2 of this series of videos I'm doing on this repair of this HP 6038A auto-ranging power supply. 0 to 60 volts, 0 to 10 amps, 200 watts. So in the first video I did, if you guys hadn't seen it, we found the fault that was occurring with this, or the reason for the fault. So first, when we powered it up, all of the indicator lights came on. All the 7-segment LEDs were on. It almost looked like an issue that you would see with a bad micro or a faulty digital circuitry. So we found what that issue was. It was a shorted capacitor that filters the unregulated 20-volt supply, which also feeds to the 5-volt bias voltage, supply voltage. So, we've replaced that capacitor, and I still need to replace it with with one that is of a suitable voltage rating. But we replaced it, fired it up, and the front panel control board it started responding to commands, which is good. That's where we left off. So in this video, I was hoping to do a bit, some further testing. I'm going to replace that cap, like I just said. Yeah, do some further testing of the boards, the control board. Go through the troubleshooting that the service manual provides, and check some of the other test points. Review the calibration procedure, see if I can handle that with what standards I have in-house. And then kind of just go through like a performance evaluation, see how this thing handles at a max load with my electronic load. Check some of the rise times for the voltage settings under load on the scope. And yeah, just do an overall performance evaluation. So that's kind of what I had in store for this video. We might find some other things that are wrong with it. I really haven't, since the last video, I really haven't checked or used it in normal operation. So I'm not sure if it's working fully now. So we're gonna probably discover that as well throughout this video. But yeah, that is the plan. So yeah, there were a few people who commented on my first video, offering, some suggestions on the repair, and also providing a bit more information on the internal circuitry, which, I really appreciate comments like that. I really appreciate you guys who took the time to write those and provide suggestions. Look, I don't try to pass these videos off as tutorials or how-to videos, because I'm still learning. Although my role here in my job is, I'm called an engineer, most of what people who do in my role or positions like it, they really just swap parts. Like, for example, when it comes to an issue with the main board, they just swap the board. So really all this stuff I've kind of taught myself. Trying to troubleshoot at the component level is something I've been teaching myself on here. And, so what I'm saying is I still have a lot more to learn. So I really appreciate those of you who comment and offer more of your input, you guys with more experience, because that's one of the reasons why I made this channel. It's not really a tutorial or how-to series of videos. It's more of just a video blog. So yeah, I just wanted to say thank you to those of you who allow me to learn more. Really appreciate it. But yeah, so that's the plan. We'll see how far we get, and yeah, so let's get started. Okay, so I got the replacement cap in of the suitable voltage rating. This nice Rubicon 35 volt 2200 cap, so that'll do just fine. Yeah, I thought I had something like that here. I mean, I better have something. I mean, look at all these electrolytic caps that I've gotten over the years. So in one of those kits, I sure as hell better had something, and sure enough I did. So that's good. Also, I just got in this desolder gun, and I used that to remove the caps, and the cap, and it worked amazingly. I've always wanted one of these, and for the longest time I was just using my iron and solder wick to remove components. So this will be really nice to start using, and it worked great. It's the Hako FR-301. Yep. Came with this nice cleaning tools and a nice case, which was really great. So, yep, we can keep moving on. Okay, so I've got the unit set back up in that main troubleshooting setup that the service manual suggests you use to troubleshoot the power section of the unit. So again, just to reiterate, right, with that setup, they have you connecting an isolation transformer to these test points there, TP1 and TP2. Okay, so that's what I've got connected to that little terminal strip, which then goes on to my isolation transformer over there. So they have you do that. Also, they have you set that switch right there from normal operation to test, that S4 switch. Okay, and then for they also have you set up a external power supply, which I'm using this HP E3612A. They have you connect that to the AC receptacle, and that's the receptacle right there, and that's where the EMI filter for it would connect at the line and neutral connection. So that's what I have connected there. And again, they do that so you have a bit more control over the bus voltage for the power mesh board. So normally that's sitting at about 320 volts DC. That way you can control it to a much lower voltage using an external power supply. So if there is any issues there, you don't, do any, you mitigate the damage that could be caused. So that's what we got there. And then on the outputs of the supply, they have you connect a 50 ohm 10 watt resistor. I don't have a 50 ohm 10 watt resistor, so I'm using this 68 ohm 50 watt resistor on the outputs. So they have you do that as well. They also have a specification for these tip switches on the GPIB board. Those are set correctly according to the service manual. And yeah, so that's what I was doing in the first video at my home. And actually, someone had pointed out with my power supply at home, I had mentioned I couldn't, because the service manual suggests they want you to use a power supply that can get up to 40 volts DC. My supply at home can only do 30 volts. However, someone had astutely pointed out that that power supply is a triple output supply with two 30 volt outputs that you can set up in series. So I had completely forgotten about that, so thank you to that person who pointed that out. I don't really use my equipment at home too often because I have all this equipment here, but yeah, that's what I love about posting these videos. Like I said earlier, is people much smarter than I can give me suggestions and tips. But yeah, so we basically replicated that setup again, and we're gonna. I think what I'd like to do is just kind of go through and do some of the troubleshooting testing. Because yeah, we did verify that the bias voltage supplies are there. But a few other things we haven't checked, like, are the DC converter. So, you know, that is one thing I'd like to check. Um, let's see, troubleshooting the AC turn-on circuits. We can maybe take a look at those, but that's really more so interested in the troubleshooting. I mean, checking the DC to DC converter test points. So checking those MOSFETs to make sure that they're switching properly. So yeah, checking these test points here, and I believe we can even check again, like, some of the waveforms for the bias voltages. We didn't look at those, so we can check those. Yeah, here are the waveforms for the DC to DC converter test points. We can verify that we're getting those. Let's see. Yeah, troubleshooting the control voltage circuit. We can maybe take a look at some of those. The current control. I'm sorry, constant current, constant voltage, my bad. We can look at those. Over voltage protection. And then the PWM and clock. So I'd like to take a look at some of these test points before we kind of go into more of the performance testing and calibration. Calibration is going to have to. I was looking at that actually, and that does require a GPIB controller, which I do not have. I actually did order one of those because, well, one, for this, and a lot of my equipment does have a GPIB controller, which is quite common on older equipment. So that'll come in handy for a number of different reasons, but we'll have to wait for that to come in to do that, because you send signals. You basically put the supply in different configurations using that controller. That isn't possible using the front panel controls, so that'll have to wait. But let's do some of these, and we can maybe kind of, based off of what we find, if we find something wrong, that'll lead us in another direction. But yeah, let's get started. Alright, so we're going to check some of the test points on the DC-DC converter circuit. So right now, the setup for that, for checking the DC-DC converter, it requests that you set the external power supply to 40 volts DC, and then on the unit itself, it has you set it to at least the current to at least 1 amp, and then the voltage to the max voltage is 60 volts, and that will actually cause the unit to go into to over range, and that's just that's the requirement for these waveforms, these test points. So checking, we're going to check PWM on and off on the HUJ3 connector. So this should be on. Okay, that looks good. And then off. Check that. Not. I really don't like probing this connector. I think that you really should get a connector that connects to it to make it easier, but that's what we should be getting for PWM off. So both these look good. Now we can check the N-channel MOSFETs to see if they're switching properly. Okay, so now we can check the N-channel MOSFETs Q3 and Q4 on the power mesh board for just see if they're switching properly. So we're going to probe the gate and the source of Q3. Okay, and that looks good. Oop. So we should be seeing that square wave at 20 kilohertz. Yep. Now Q4. Yep, that's looking good. Alright. Alright, so now we're just going to check drain to source. Again, just to see the switching. Alright, that looks good. That's Q3. Let's try to get Q4. Oh, there's Q4. Alright. Looks good. So, I wanted to check the bias supply voltages for ripple and check out the 5-volt bias supply voltage. Look at that. Now, its VRMS is 5. It's accurate in that respect. But look at all those peaks. And if we AC couple it, we can get a better look at that signal. I really dislike probing this connector. Oh man. Yeah, look at that. What is going on there? You know, I have to check the service manual maybe to see, maybe it explains what that waveform is, but it's very strange. And the other, because we can look at the other supply voltages, bias supply voltages. So this is 15, for example. Oops. And again, we're in AC coupling, but we can look at it in DC coupled too. Jesus. Sorry. This connector just, there's really, yeah. I mean, peak to peak 40 millivolts, you know, I mean, it's really clean. Yeah, see? So that's the plus 15. And so then we can look at minus 15. I'm so sorry. And again, yeah, I mean, there's no ripple or anything, but that plus 5, I mean, really odd. Yeah, I'm gonna have to look into that further to see if that's normal or not. Just thought that was interesting. Just figured I'd go through and double check all of the test points that the service manual offers for troubleshooting the plus 5 bias supply, and yeah, so these have to do with the PWM U6, and right now I'm actually doing this test point here, U6 is the PWM, probing pin 12, 13, they're tied together. And we should be seeing a 19 volt peak, 15 microsecond pulses at 45 kilohertz. And yeah, that's what we're seeing. So that looks good. And we'll check a couple of the other ones just to make sure everything looks good. You know, again, I'm not really too sure if that is what we should be seeing, those spikes, those positive and negative spikes on the 5 volt bias rail. Alright, so now I'm actually probing the first node, which is A2U, again on the PWM U6 pin. Now this says pin 6, but I'm actually probing pin 7. I tried probing pin 6 and I don't get what they've displayed here, and I do get it on pin 7. So pin 6 is the timing resistor for this PWM, and pin 7 is the timing capacitor. Okay, so I think either this is maybe a mistake, or maybe there is something wrong, but yeah, so so this is what we have on the scope, and that is what they've got there as well. So you know, a 45 kilohertz sawtooth wave, peak to peak, anywhere from 2 to 4 volts. Yeah, so that looks good too. Again, with the exception of that discrepancy there between it being pin 6 or pin 7. Don't know if that's an issue or if that's a typo or what, but just maybe something we should notate. Moving on down the line here, so now I'm probing Q3, transistor Q3 on the emitter, and we should be seeing a roughly 20 volt peak at 5 microsecond pulses at 45 kilohertz frequency. So look at the scope. That's about what we're getting again. So peak to peak, and a little, I guess it says roughly. I don't know what that range should be, but pretty close. 22 volts. Yep, definitely. We're at 5 microseconds per division, and you can see that pulse is about 1 division wide, and that frequency is at roughly 48 kilohertz. The frequency, they've been specifying 45 kilohertz, and it's been, off by 1 to 2 kilohertz, I've noticed, and I don't know how accurate that needs to be, but everything is looking good so far again, so that's, yeah. Alright, so now it's asking us to check a voltage reference, 2.5 volt reference voltage. This is not the reference voltage that is on the J3 connector. It's actually a voltage regulator, a low voltage regulator, MC1403, I believe, which is U5 on the control board. Takes the 5 volt reference from the PWM U6, brings it down to 2.5 volts. So we should be seeing 2.5 volts on VIN of U5. Okay, and yeah, we're seeing it's 2.5, 2.6, but it's a clean signal. And then we can even check VIN, and yeah, 4.8, 4.9. So yeah, that looks pretty good. So again, everything's looking good so far, or fairly good. Okay, so now we're probing at between R46 and R47 on the control board. We should be getting 2.5 volts here. And this is actually just a voltage divider. You can see it on the schematic. So we're probing right here. Yep. So we should be seeing 2.5 volts there. And yep. So that's what we're getting. And no peaks, no strange pulses. So yeah, I mean, that's all of the test points that they give you to look at. So, you know, I'm not sure. Again, this might just be normal. I mean, here's the description for it. It says PWM U6 includes a clock generator, 45 kilohertz, set by the timing resistor and timing capacitor, and a current limit, which is set by R50. It turns off each output pulse using the difference between the voltage at voltage divider R46, R47, and 2.5 volts set by voltage regulator U5. So yeah, I you know, I don't know, because both those look nice and clean. We probed both of those. So yeah, I don't know. It could be normal. But yeah. So I just wanted to run a quick little test before we go down too much of a rabbit hole here, and I probably should have done this a little bit sooner, but I decided to probe right here to check the 5 volts at this jumper W2. Now, where we were originally probing, where we saw those peaks on the 5 volt rail, is actually right here, J3-1. That's that connector, and you can see that there's a 10K resistor between that test point and the 5 volt rail. Now it's still at 5 volts, but you know, that's the only difference. And you can look at the scope, those peaks have disappeared. Alright, and we can even put it in AC coupled. Sorry, this guy's in the way. Okay, so yeah, so we're not seeing those peaks, and I mean, they were readily apparent even at 500 millivolts per division. So I think we're in the clear. Not sure why that you're seeing those peaks on that 10K resistor. Maybe somebody might have some input there, but I think we can move on. But it was still a good thing to check. Alright, so moving on, as I mentioned in the last video, or maybe I can't remember if I mentioned it earlier, there are 2 other bias voltages that we didn't test in the first video, and one of them is mentioned in the down programmer troubleshooting section. The down programmer circuit allows the unit to drop the voltage rapidly if need be, and so we can measure it on U4, which is an LM317, 8.9 volts. That's what I'm probing now, and you can see we got 8.86, so that's looking good. Nice clean signal. And so we can move on to the next one. Okay, and now the final bias voltage is discussed in the over voltage protection circuit troubleshooting section. So it has you probe U9, the out pin, which is U9 is just an MC1403 as far as I can tell. So that's what we are probing now. Alright, and you can see we've got, it's about 2.49, 2.495, so that's close enough. Nice clean signal, so we are good to go here. And so that's all the bias voltages. You know, everything's looking good. I think it'd be neat to probe some of the PWM and clock signals next, but after that, I think we're good to start maybe doing some performance testing, check some of the, the output voltage accuracy, some things like that. But all right. So we moved on to the clock and PWM circuits, and right now we're going to be taking a look at the clock circuit, which is a 20 kilohertz clock, and we're probing A2U21 pin 7 and A2U22-3. U21 is an op amp and U22 is a 4-bit binary dual counter. So let's take a look at the waveform for these. So I believe it was pin 7 is on U21 is a 320 kilohertz square wave, and U22 pin 3 is 160 kilohertz square wave, and I've actually got both channels on, so 2 probes, and yeah, so probe number 1 is probing the 320 kilohertz signal, and probe 2 the 160 kilohertz, and everything looks good. And so this is probing U13 for the 20 kilohertz signal. So we've got a 20 kilohertz square wave on the scope. It's looking good, and this should be no surprise to us because when we were probing the N-channel MOSFETs on the power mesh board, we could see them switching at 20 kilohertz. So that would be that would indicate that the PWM is working fine. So this should, we should expect to see this. But I think with that, we can now move on to doing some performance testing on this guy. Okay, so I figured we could do some performance testing now with the instrument after we've checked all those bias voltages, and it seems like everything is working in good working order. And so, I checked the service manual because it does have some performance test procedures. Now, as I said earlier, the calibration procedure is strictly done with the GPIB controller, and even some of the performance tests are done with that controller as well. So the service manual does provide a few tests that can be done with just using the front panel controls, and one of them is a load effect test, and this is the setup that it has for the test. So you've got an electronic load on the outputs of the instrument, and then a digital voltmeter is connected to the sense outputs, and what they're signifying here with the circles is actually a coaxial cable. Now they also have this what looks like a current monitoring resistor between the negative terminal of the output and the negative terminal of the electronic load, and it says to DVM. So that's kind of confusing me a bit. I don't know if that's monitoring current, if that connects to that digital voltmeter. I'm not really sure what they're getting at here. So I kind of, and if this is obvious to you, please let me know in the comments. I mean, as I said earlier in this video, look, a lot of this testing I'm doing for the first time. I've never really done any performance testing with a power supply before, or not, at least not these tests. So, I'm learning as I go here. So please chime in if you know what they're actually trying to accomplish with this test. But anyway, I did find this article, or I don't know what document. It is by Agilent, and it provides basically a series of tests. It's talking in a general sense about testing power supplies and the tests you can do. And so this is their setup. And this is for a load transient recovery test. So you've got the power supply here, then there's a scope on the outputs, and then the electronic load. This makes more sense to me. You've got some example waveforms here. So this is when the load drops drastically. You're going to see a rising peak in the output voltage, and then if the if the current is rapidly increasing, you're going to see a drop, a small peak going negative. Okay, so in that time, that the peak, the time there, that's the recovery time. So that is currently what I have set up. So if you look here, still got the power supply. I don't have the cover on it. And so this is what I've got. Now I still have the voltmeter connected to the sense output, and it even comes with this BNC connector, so you can connect it to a BNC cable, coaxial cable. I have that going to my digital voltmeter, and then I also have my oscilloscope connected to the sense outputs as well. And actually, right now on the display, this is an example of the a test that I performed earlier. So you can see here, that's the peak from when the load rapidly decreased. And so what I'm doing here is I'm using the single mode trigger mode on the instrument. So if you look here, if I click mode, it's listed as single, so it'll take a single snapshot of the waveform. And then what I was displaying earlier was the cursor measurements, so that way I can measure the time from the rise and the fall of the peak, and also I can measure the voltage, the peak-to-peak voltage. So that's what we're going to do. And so what I'm going to do is I'm going to turn the load on and press the run button at exactly the same time, so it should capture the waveform, that transient recovery peak. That may not be the best way to do it, but it has worked. And I think it's because the transient recovery time is on the order of milliseconds. So, you know, if it was something that we were trying to capture something that was on the order of microseconds or nanoseconds, this probably wouldn't work, but that's what I'm going to be doing. And if you have a better way to do this test, by all means, again, put it in the comments. So that's what we're going to do first, and we'll just kind of make our way either through this document, or we'll take a look at some of the other performance tests in the service manual, and if the setup makes sense to me, we'll do those. But that's what we're going to do. Alright, so for the first test, this load transient recovery time test, I figured we're going to do it at max voltage, so that's 60 volts for the supply. And so at max voltage, the max current is 3.3 amps for a total of 200 watts. So that's what we're going to do now, and we should be seeing a negative peak. That's going to be the transient recovery time. And so I'm going to turn the load on now and trigger the scope for a single shot right now. Okay. Yep. And so that peak there, the distance from from here to here is going to be the transient recovery time, and we can measure that using the cursors of the scope. So, excuse my reach. Okay. You can also measure the voltage as well. Okay, so we're looking at peak is 30 millivolts, and then the recovery time is, let's see, delta T is 116 milliseconds. Okay, so that's the transient recovery time for an increase in current. So we can do the same thing for the from decreasing. So let's just change the trigger. So we're going to be looking for a positive peak. And then I'm going to do the same thing again. I'm going to turn the load off, and we should see a positive peak. Alright, and so again, that peak there would be the transient recovery time, and we can measure that again. I believe T2, yeah, T2 is in the right spot. And obviously we'll have to change V2. Bring that up. And so delta V is 15 millivolts and 148 milliseconds. So now for this supply, low transient recovery time, they give two specs. For a 10% load change, it's 1 millisecond to within 75 millivolts of the set point. 50% load current change, 2 milliseconds to within 200 millivolts of the set point. So we are well within the spec. I mean, because it's not, I mean, unless someone can correct me here, but the set point isn't changing by more than 30 millivolts, I believe, when the load was turned on, and 15 millivolts when the load was turned off. So that, I believe, is well within the spec, and we're talking about a load change from the max to 0 and vice versa. So I believe that's within spec, but if I am getting that wrong, please somebody correct me. Now let's take a look at some different set points and check the transient recovery times. Okay, so now I've got it set to the power supply is set to 40 volts and a max current of 6 amps. Now you might be saying to yourself, well, wait a second, that's 240 watts. I thought the supply could only do 200 watts. Well, if you look at the service manual, and it provides a graphical representation of the max output. And so at 60 volts, it can do 3.3 amps for a total of 200 watts. 20 volts, it can do a total of 10 amps for 200 watts. But in between there, those voltages in between, the max output can be a little bit higher than 200 watts. And so it maxes out at 40 volts, 6 amps, 240 watts. So let's give that a try and take a look at the transient recovery time for that. Okay, wow, and you can see, check out that peak. So let's see if we can get a measurement there. So we're looking at 86 milliseconds for the transient recovery time. So V1 is good where it's at. Let's change V2. I mean, again, you can use the divisions to figure that out as well, but, you know, so we're looking at 52 millivolts roughly for the peak to peak for that transient peak. And so again, that is still within the spec. Again, if I'm reading that correctly, the supply hasn't changed by greater than 75 or 200 millivolts. And we're looking at 52 millivolts here, so we are still looking good. Now let's repeat this again, turning the load off. Okay, so again, you know, I'm not going to do the measurement because we'll just use divisions, but you can see, looking at 20, not even 40 millivolts. So again, it looks like it's within spec for, this is definitely going to be the max output of this supply at 240 watts. So it's looking good. Okay, so I think the last transient recovery time test we're going to do is at the other end of the voltage spectrum, so at 20 volts, 10 amps. Let's see what we get for this test. Oh wow, so check that out. I'm actually... Yeah, so wow, look at that peak. Let's just take a quick look here. Yeah, so we're at 60 millivolts there for the that peak to peak for that peak. Again, still within the spec. Then we'll just do the turning the load off. And yeah, so again, it's about 40 millivolts, so looking good. Alright, I think now we can move on to another test. Let's see what that document has, or the service manual. Just wanted to show you guys the specs for the supply so you can see what I was referring to. So for the load transient recovery time, 10% of the load change is 1 milliseconds to within 75 millivolts. 50% of the load change, 2 milliseconds to within 200 millivolts. And again, you can see that we weren't changing by anywhere near either of these values for any of the tests we did. It says the time required for the output voltage to recover within a band around the nominal voltage following a 10% or 50% change in load current. Now we did 100% change in load current. So I would imagine that these would be even greater for those, for 100% change. So I think this is a good indication that the supply is operating well within the specs. And so next thing we can look at is load effect, which is, spec is here, voltage 0.01%. So we're looking at, let's do 60 volts, that'll be pretty much 6 millivolts. And so the test setup for that is pretty much what we already have. So we got the DMM connected here, and well, we're going to use the scope. Well, I guess we can use the DMM. So let's give that a try. We'll keep the scope on there though, and we can take a look. All right. Okay, so we're going to be monitoring the DMM while I do this, but I'm also going to capture it on the scope so we can also take a look as well. So right now I'm going to apply it's at 60 volts, as you can see. We're going to apply a 3.3 amp load and see what happens to the voltage. Okay, so now it did drop about 8 millivolts, I'm sorry. But you can see it recovered right back to where it was. Now, that load effect, you know, it doesn't count that drop. That's the transient. So, if it was out of spec, it would now be sitting at, for example, 59.993 or lower. And you can see it's returned right back to where it was without a load. So that, again, is a good indication that the instrument is operating within spec. And so again, this is what we captured when we did that test while we were looking at the the DMM. But you know, you can see that yes, there is that transient peak there, but the voltage, output voltage, returns right around where it was initially. So, you know, this supply, even at max current, is operating, or max output, it's operating where it should be. Okay, so the next test I figured we'd do is a PARD test, which is periodic and random deviation, which it used to stand for ripple and it used to be ripple and noise. But that's basically what we're looking for here on the output under a load. And so this is looking at the service, looking at that Agilent document, but the service manual has a similar setup where you have these coaxial cables with a 50 ohm termination connected to the outputs of the supply, and then also they've got a blocking capacitors as well on the output. So, I wasn't really quite sure how to perform that setup, so this is what I've got. I've got my probe connected to the output with this 50 ohm termination here, and then this is actually pretty similar, I believe, to what, if you ever look at Dave at the EEV blog does a video on ripple and noise measurements on a power supply, and it looks like he uses a similar setup. So that's what I went with here. And so right now, as I showed you earlier, we got 60 volts, 3.3 amps, or 3.4 amps, and this is at, again, the full output of the supply. And this is what we've got on the scope. So now you can kind of see, you can just barely, I'm using the cursors to measure this because it's really hard to trigger on this, but that's the ripple right there. You can just make it out 120 hertz, it looks like. So yeah, but you can clearly see there's a lot of noise. If we go to voltage, so yeah, we're getting some peaks, peak-to-peak measurements, upwards of 60, 70 millivolts. Now, there is a specified bandwidth for this measurement. I believe it's 20 hertz to 20 megahertz. So right now, I've got the scope limited, the bandwidth, to 20 megahertz. And it does appear that this noise is coming from the supply. If I shut the supply off, I get a really nice clean signal. So it doesn't appear to be our connection that's making these peaks. And the specs for the supply, it has a spec for both peak-to-peak and RMS. So peak-to-peak, it's 30 millivolts, and then RMS, it's 3. We are actually meeting, it looks like from the scope, we are meeting the 3 millivolt requirement, where it's fluctuating between, around 2.5 millivolts, but not the peak-to-peak requirement, and but I still think this looks pretty damn good for a power supply that is from the late 80s, and obviously it might still need some work. I mean, there are obviously some refit caps that we still need to replace. We've only replaced that one capacitor, so yeah, I mean, I think we're still looking in pretty good shape here. Something else that I thought was pretty neat. So if I put this the measurement mode in average, so that kind of averages out the signal, and it's a good way of taking away some noise if you've got a really noisy signal like we do here. It's kind of cheating, I guess, if we were to use the measurements for the actual, apply that to the specs. But something that I thought was really cool is, if you look here, you can see these peaks, and you can see that they're at a frequency of 20 kilohertz, which is the same frequency that the PWM and the MOSFETs are switching at on the DC to DC converter. And I'm just curious if that's actually what we're picking up here. If it is, that's pretty neat. But yeah, because it doesn't, you don't really see anything, any symmetric, or, everything else looks kind of like asymmetric noise, but except right there, yeah, so I don't know. Just thought that was pretty neat. Well, guys, I think that might be it for this video. I mean, we did all the performance testing that we could do. Again, some of the other performance tests specified in the service manual, there's a constant current and a constant voltage accuracy tests. They require the GPIB controller, which I don't have, and of course there's the calibration of the supply as well that needs to be done using that controller. You know, I did order that, and like I said, and I don't know, I might do a video on that once it comes in. I don't know how interesting of a video that would make for, but I've never used one of those controllers before, so it could be pretty cool. Also, another thing I do have to do to this supply before I put it back together is replace those reefa caps. So I do have some replacements there, but you know, again, I don't know. You know, that's not all that interesting, but yeah. So we did, to kind of sum it up, we found the initial fault. It was that C23 capacitor on the control board. Replaced that with the suitable voltage rating and capacitance, and did some performance tests. We kind of went down a little bit of a rabbit hole with that 5-volt bias voltage, those weird peaks that we were seeing. But yeah, you know, and then followed it up with the performance tests, which, you know, looked really good. And so I think I'm looking forward to adding this supply to my arsenal of power supplies, which isn't all that great, but this definitely will provide some additional power as far as the amount of current it can put out. So yeah, I hope you guys found that interesting, and you know, if there's any suggestions that you guys might have for anything that I did in this video, or what else I can do moving forward, I'd really appreciate it. I really appreciated your comments that you gave on the first video I did on the supply. Thank you guys for taking the time to write those and watch. So yeah, we'll I'll catch you guys next time. All right.